Hello, my name is Naseem, and in this video we will talk about binomial distribution, means probability distribution. In last video, we already talked about how we can create binomial distribution for the random variable of a sample space which we have, and with the help of a specific random experiment, we implemented the formula. So once again, let me revise the fundamental of implementing binomial distribution formula. We were having a coin, a fair coin. We used to have head on one surface of it and tail on second surface of it, and it is a fair coin. And we are considering success means every time we are getting head, we are considering it as a success, right? And every time we are getting tail, we are considering it as a failure, right? And the probability of success is, we are already given, it is P, and the probability of getting failure is, it is already Q, and the relation between P and Q is equals to 1 minus Q, right? This is what the probability relationship between these specific experiment. Now we have given, means what we are doing, we are tossing this coin 3 times, all right, and we are noting down the surface, means which we get, means the outcome of the coin we get in these 3 attempts, and we are just creating a sample space for us. So these were the all the possible outcome of the sample space which we have. And next, what we have done, we got a random variable which is x, and the statement of this random variable is number of heads appear, and we already talked about head is a success, so we are interested in finding out number of success we are getting. So the possibility of getting minimum number of heads means failure is 0, and again we have 1, and at the same time we have 2 and 3. 3 is the maximum possibility of getting all 3 heads in all 3 attempts which we are doing. And because we have P and Q as the probability of passing, means probability of success and failure, we created the probability distribution of this specific random variable. So the probability of getting 0 means no heads, and this was the favorable outcome of this, and for this we got a probability Q raised to the power 3. So number of favorable outcomes in this sample space to this specific condition means getting minimum 1 success, means getting minimum 1 head. So this was the one thing. Second and third, so we have these 3 different outcomes which are favorable to this specific condition. So as a probability of it, what we find out is that 3q raised to the power 2 and multiply p. Same time, if we are talking about the number of outcomes which is having 2 favorable outcome, which is heads, this is 1, 2 and 3. These are 3 different outcome favorable to this specific condition, and as a output means probability of it, what we find out 3p square q. And when we are talking about 3, means all of the coins in all 3 attempts we are getting head. So this was the only which is favorable to this specific condition. So we got p raised to the power 3. And when we go into the deeper of this thing, what we find out that the probability of any x between experiment, how we can calculate the probability. So this was the formula we got, and we call it binomial distribution. If you don't know how we calculated, how we implemented this formula, just go to our last video and you will find out with the explanation of it. Let's begin with the further study of this binomial distribution. So in this specific example, if we talk about what is the probability of getting 2 of a random experiment, of 2 heads of a random experiment when we are tossing 3 different coins. Here for this specific example, n would be 3, because we are talking about the maximum number of outcome, means the maximum number of outcomes is 3, and we are interested in finding out x equals to 2. So just put this formula, this value into the formula, and we will find out p of 2, means directly we will find out p of 2, this one. This is how we can calculate probability of any event of the random experiment which we have done. But there is some limitations of it. What are the limitations? So prior to going directly into the limitations, I would try to understand why binomial distribution is actually a mother of Gaussian or normal distribution. So let's consider different scenarios. So let's consider an experiment where we are doing, means we are tossing only 2 number, means this coin 2 times. In last example, we have tried by tossing this coin 3 times, but this time we are tossing this coin 2 times, right? So the sample space would be HH, HT, TH, and in the same way TT. If we talk about what is the probability of getting 0 success, means there is no head in the outcome, for this. So this would be the probability, means near about 0.25. In the same way, if we talk about what is the probability of getting 2, means both of the outcomes as a head, means the success. So again 0.25 would be the probability of it. And the maximum probability in this experiment would be getting at least one success item, which is head. In these two outcomes we will get at least one head, and the probability of it is about near about 0.5. If we add this probability 0.25 plus 0.25 plus 0.5, finally we will get 1. Alright, this is one thing. We are repeating the same experiment with the higher number of success item. This time we are tossing one coin 4 different time, single coin 4 different time, because n is 4, and we are interested in getting 0 success, then getting 1 success, means at least 1, at least 2, at least 3, at least 4, means all of the 4 items are showing head. Again we got it, means the probability distribution, means binomial distribution of this specific experiment will be something like this as we are having on the screen, right? So getting 0 item will be there will be a possibility, the probability of it would be somewhere between 0.05 and 1, right? In the same way, if we talk about probability of getting at least 1 success, means at least 1 head in this experiment, at least 3 head on this experiment, so the probability would be 0.254. The maximum probability in this experiment would be getting at least 2 heads, means 2 success, and this would be somewhere 0.35, between 0.35 to 4. So this would be another experiment. If we repeat same experiment with 12 different repetitions, means we are tossing single coin 12 different time, we are tossing 1 2 3, means 12 different time, and we are writing down the outcomes of this experiment. So this will be the sample space, this would be the graph between the probability and the number of success items we are getting. So for 0 success there would be at least somewhere equals to 0 probability. For 1 success there would be somewhere between 0 and 0.05, and in the same way probability is increasing from getting 0 success item to 6 item, and again it is decreasing from 6 to 12 once again. So what we are analyzing is that as we are increasing the repetitions of the experiment, we are getting a specific graph in a form, and this graph is actually saying us something very specifically. We call it Bell graph. This graph is actually a mother of Gaussian distribution. Now let's talk about limitation of binomial distribution. So let's talk about first limitation. So every time, means the probability, means the formula of binomial distribution is P, means probability of x. X can be if we talk about specifically with this experiment, where we are just repeating our experiment 12 times, so the n would be n would be 12, and x would be somewhere between 0 to 12, and the formula for getting probability of any x between 0 to 12 would be n factorial, and then n minus x factorial, and then p raised to the power n and q raised to the power n minus x. This would be the formula for getting probability of any specific item, right? P is the probability of success and Q is the probability of failure. We already talked about in our last video. It is okay if we are repeating this experiment for 12 times, 13 times or 50 times. But when we come with the real case scenario, means when we are working on a real project of a machine learning, when we are implementing some machine learning algorithm, we have data in the form of the size of the data might be gigabyte. There is a chance we have some sales or marketing data, and in this data we have an Excel sheet, and in this Excel sheet we have, let us say 1,000 columns, and these 1,000 columns are the parameter for this n, and we are interested in finding out probability of any one parameter of it. Means I am telling you the possibility of getting a data in this specific form. When n is very high, as the n is increasing in this formula, computation of the data is increasing accordingly. No matter we are doing this computation on our paper or on our Excel sheet or on our computer, it would be very hard to calculate the thing. So this was the first limitation of binomial distributions. Mean as we are increasing n in this formula, right, the computation of the data will be very high, and it will be very very complex to compute the thing for us, because in real time, in real scenario, we already talked about it, there may be a chance of getting very huge Excel file or 1,000 number of parameters of a data which we are having, means the historical data I'm talking about. So we must have some other approach to calculate the probability of the data points which we having. All right, so this was the one limitation of the binomial distribution. If we talk about second limitation, so the second limitation is that it is this binomial distribution is discrete distribution in nature. By discrete, what I mean to say is that we can have, let's talk about once again about this specific use case where we are just tossing a single coin 12 different time, right? And we are interested in finding out probability of getting 7 different success, means 7 different head in this experiment, or 8 or 9, or between somewhere between 0 to 12. But we cannot tell about the specific amount of probability we are getting, because this experiment was discrete in nature. We can have only one, means only 2 output, which is head and tail. So this is some type of discrete use case. We cannot talk about continuous output, continuous probability, or continuous input, because we can get number of head, means number of success, in the form of 0, 1 or 2. We cannot get something like 1.5, right? But when we come into the real scenarios or the real projects, when we are working on to the in our organization, what can be the scenario that the data we are getting would be in continuous form, all right? And for the continuous data, we must have something in our hand to calculate probability for the continuous data as well, right? But in this is a diagram of binomial probability distribution, it is not continuous, but it is distributed. It is discrete in nature. As you can see, we can calculate probability of 1, 2, 3, but if someone says us what is the probability of getting somewhere between 2 and 3, so we are not able to talk about that specific probability, because this is discrete in nature, right? So this is second second limitation of this binomial distribution. Due to these two limitations, we must have something else in our hand, right? And these two limitations actually give birth to the another distribution, which we call Gaussian distribution or normal distribution. This Gaussian or normal distribution is something which we can use while implementing machine learning algorithm for our specific use case, right? So let's just talk about this Gaussian distribution. You can see we have a Gaussian distribution, means we have from minus 20 to 20, as you can see here in this screen, right? And what we calculated, we have 3 different things of this data set, which is mean, standard deviation, and variance. And we can set this mean, standard deviation, and variance explicitly. Currently I have defined mean as 1, and I have defined standard deviation as 4, and the variance is 16. Because relation between standard deviation and variance is because in standard deviation is itself is the under root form of variance. So under root of 16 would be 4 automatically. So I have implemented the formula here. So as you can see, I have drawn a normal distribution diagram for you on this typical data set which we have currently on the screen, right? I have calculated mean, means the difference between x and mean, means deviations, these are called deviations. We already talked about it. While calculating standard deviation, we must calculate mean, and then we have calculated probability distribution, mean normal distribution, and this is how we are getting. So there are something we need to talk about this specific distribution. First thing I will talk about is that it is continuous in nature. It is continuous in nature. It is not discrete. So the very first problem which we are facing from the binomial distribution means it cannot be used for the continuous data. But this normal distribution we can use for the continuous data as well. The formula of normal distribution means this is the formula. Here nx is nothing but the px. We can write down px equals to 1 divided by 2 pi, right? Sigma square. This is sigma square is nothing but the variance under root of it, right? Raised to the power half or under root is exactly same. We have exponential of it, and this exponential we have minus x minus mu. Mu is again the mean of the data set, and divided by 2 sigma square, again variance. So this is the formula. This is nothing but the formula which we have. Now as you can see on the screen, this is the normal distribution of the data set which we have used. Means this is the synthetic data we have used for understanding of this of this lecture. I have mean which is 1, right? And I have a standard deviation which is 4, and I have variance which is 16. If you see, there is something, means the maximum tip of this diagram would be somewhere 1, means mean of the data set which we have defined. If I change it it is flexible in nature. If I change 1 to some other value, it will be changed automatically. Let's try to change it. So it is changing. If I changed it to 10, it is flexible in nature. From 1 to 10, it is already changed itself, as you can see right now. So this is how it is actually changing. And if we wanted to find out the probability, and one more thing you can see here, it is actually starting from -20. So you can see this line, and it is ending till 20, because we have data set started from -20, you can see here, and it is completing to 20, as you can see right here. All right, so it actually tells about, we can calculate probability of any data point which we have, but it cannot tell about for someone. For example, someone tell us what is the probability of P15. The probability, if we go back and we write down some line, and we can directly say that this is the probability something between 0.04, which is this, and 0.06. We cannot calculate like this, because this is not in discrete, because 15 is the discrete currently. We must pass some limit of it. For example, if we are interested in finding out probability of 15, we must have some limitation, some range actually. So we are interested in finding out probability of 14 and 16. This way we can calculate probability, and this time there would be a calculation of the area of this specific area. Somewhere here, somewhere 14, and here is 16 I'm considering, and this would be the area of the data of this curve, and this area would be the probability of 16. We are actually approximating, right? We are not talking about exact value. So this is how we can use a normal distribution for our calculation. We need to do some calculation, some integration, differentiation, and output of this integration, differentiation, we will get area, and this area would be the probability of P15. One limitation, which was data set when we are implementing real machine learning algorithm, and this data set may be continuous in nature. So this Gaussian distribution is solving that problem first. In the second place, if we talk about the calculation point of view, this time we don't need to do very heavy calculations like we were doing in the case of binomial distribution. We are not going to calculate or do these type of complex calculations this time. What we have this time, we have a function, and we need to approximate some range of the data set. For example, if we wanted to find out probability of 0, right, probability of 0, then we need to give some range, probability of getting from -1 to 1, and px dx, and this way we can calculate probability very easily. There is no need to do very lengthy calculations. So these two limitations is already solved by using Gaussian distribution. In the description of this video, I have attached some links for you where you can download this data, some added material, and you can use this material for your further studies of getting a deep understanding of Gaussian distribution or normal distribution. So thank you for watching this video. One thing you must have in your mind, this Gaussian distribution is very important. We are going to use this Gaussian distribution throughout our understanding and implementing machine learning algorithms. Happy learning, and see you in next video.